Okay, folks, today we're going to start talking about imine formation and imine reactivity and what are some of the cool things you can do with it. The imine looks like this. It is a C double bond N. You can use ammonia and have a hydrogen instead of the R group, but those are really unstable. Now, in terms of synthesis, these are made almost exclusively through the acid and electrophile pathway. All right, so a little bit of trivia about the imine itself. It's kind of cool because I've made a bunch of these with my research over the years, and they're all it's some shade of yellow. There is something about the C double bond N functional group that makes it absorb and re-emit light in sort of that yellow spectrum. I've seen them everywhere from this barely off-white, slight yellow to really bright canary yellow. Also, once you make this, they tend toward being solids, especially if you've got something chunky up there on your R group. Now, that can work to your advantage for reasons we'll talk about in a few minutes. So, the way imines are made, generally speaking, look something like this. You start, and I'm going to start with an aldehyde. Why? Because I felt like it, and it's my video. You start with an aldehyde and you react it with a primary amine. A primary amine. Now, quick reminder of the substitution levels on amines. If the nitrogen has 1 carbon, it's primary. 2, it has secondary. 3, it is quaternary. So, the aldehyde and the primary amine react in the presence of faint catalytic amounts of acid. And what you get as your product, and this is an equilibrium process, so we're going to talk about how to make Le Chatelier work for you, is this amine plus water as your byproduct. So you'll get your imine and water as your byproduct, like I just said. All right, in terms of mechanism, this is a very traditional electrophilic or acid pathway mechanism. So what we start with, we're going to start using acetaldehyde here, and we're going to protonate it with our hydronium. Now, one thing I want you to note is all the steps of this reaction are in equilibrium. So now we've got that. As a reminder, this is our primed pump. Now, what do we mean by a primed pump? Basically, we've made this carbonyl more reactive. So it's going to be more susceptible to a nucleophilic attack by the amine. So let's go ahead and bring in the villain of our piece. Nah, amines are cool. They just smell bad. Oh, let's say ethylamine. Ethylamine does the nucleophilic attack at the carbonyl carbon, opening up the carbon-oxygen pi bond, which is in equilibrium, and gives us this. Now, one thing I hope you remember is whenever we do any of these acid pathway steps, every step of the mechanism has an intermediate that is positively charged. So here, what we're going to do is use the OH to deprotonate the nitrogen, sending the electrons back onto the nitrogen as we do. equilibrium step to get us here. Now, we've turned that OH into an OH2. As we all know, that's a very spiffy leaving group. Now, we got to find some way to knock this off. And this is going to be what separates the imines from the enamines we're going to talk about in a couple minutes. So, how do we knock this OH2 off? Well, I'm sorry I don't have more room here, so I'll do my best. What we do is we use the lone pair of electrons on the nitrogen to form a nitrogen-carbon pi bond. The lone pair of electrons on the nitrogen forming a nitrogen-carbon pi bond at the same time dislodging that OH2, kicking off our water. That brings us here. And we're almost home. We just have some way, I wish we had some way of getting rid of that hydrogen on the nitrogen. And lo and behold, ladies and gentlemen, we do. It's the water. Now, where does this water molecule come from that we are using here to do that deprotonation? Well, it can come in one of two places. It can either come as a byproduct of the water there, or it can be the water here that we just kicked off. Either one of them are equally possible. What happens is that proton is pulled off, electrons stay behind, and still in an equilibrium, this is what we get. Now, I noticed somewhere along this, and I don't know how to go back and correct my mistakes, so I'm just going to point them out right now. Somewhere along this way, I started turning this CH3 into an R group. I didn't mean to. Here, I'm going to fix it this way. See how clever I am? That was a mistake on my part. So this is the overall mechanism for imine formation. Now, let's talk about how we can get this to work for you. All right. Here's how you do it. Because the entire thing is an equilibrium process, there's a few tricks you can do here. Whenever you mix your aldehyde with that primary amine, you use trace acid and ethanol, specifically 200 proof. Now, for those of you who don't know what the proofing is on alcohol, either you're not a big fan of prohibition or that you're not an alcoholic. So what 200 proof means is 100% ethanol, 0% water. You cannot get this through distillation. When you distill an ethanol water mix, what you end up with is 95% ethanol, because the ethanol and the water azeotrope. For those of you who don't remember what azeotrope means, it's when you have two solvents that, when combined, have a different boiling point than either one of the parents. Now, the reason we want our ethanol here to be 200 proof is the product here is this imine, and let's not forget a water molecule that was created here. Not having any water in the ethanol to start with means that the ethanol will simply dissolve this water away from the reaction, and that pushes you in favor of the product side of the equilibrium. The other thing I'd like to point out about this is aldehydes, especially smaller ones, and amines tend to be liquids. But imines, not all the time, but tend to be solids, specifically solids that are not ethanol soluble, which means that these will precipitate out of the reaction mixture and give you the solid imine, and thereby really pushing this toward the right side of the equilibrium. Now, I've done a few of these, and these are actually really fun to watch because you get a stirring solution of your pure ethanol, you add in your aldehyde, you add in your amine, you add in your acid, you put it in an Erlenmeyer on a stir plate. They usually don't need heat, but if you need to, set it on the lowest possible setting. It's not going to hurt anything. And then you sit back and watch the show. You'll know that this starts working when the solution turns yellow. And then it will start to get cloudy. And then you will see the solid starting to precipitate out. When you see your solid forming, you know it's working. So, I don't know, leave it alone for a couple hours. Go get a cup of coffee, do some homework, putz around doing something else in the lab. Let the imine do its job. And then by the end, after a couple hours, you're going to have a solid imine in the bottom of your Erlenmeyer with unreacted aldehyde and amine in the ethanol solution on the top. So all you do is filter this and wash the solid with water. And there's your imine. It usually does not require any further purification. So that's all for today's lesson, ladies and gentlemen. One of the things I'm going to tell you that's coming up next is we are going to talk about enamine formation. Why enamine? Because IUPAC hates you.